Hey everyone, welcome back. This time we're going to chat about how to compare means of two conditions. The good old-fashioned hypothesis test. All right, let's get into it. So, examples of this kind of approach are students' t-test, which is what we're going to talk about, but there's many others. So another typical approach is the analysis of variance, the ANOVA. So t-test compares group A and group B. An analysis of variance compares as many groups as you would like. And there's all kinds of flavors of ANOVAs. So I cannot introduce you to all this stuff because, again, you should take some fairly extensive probability and statistics courses over the next couple of quarters. But I just wanted to give you the flavor that there's many different ways to check what is the central tendency of group A, of the diabetics who are controls and are not getting treated. And what is the central tendency of group B, the diabetics who are getting this medicine. Okay? So that is what we're concerned with today. So, students' t-test. The t-test is looking at means. It's looking at, does group A have a different mean than group B in a way which is significantly different? Okay? So fundamentally, how would this work? Let's use a clear example. So we have two curves here. One is a distribution of females, that's in the blue, and the other is the males in the black. And this is one of those density plots, right? So what you're seeing is that, along this axis, come on, Jason. There we go. Along this axis is height. Height apparently in inches by those numbers, right? And so most males are peaking somewhere around that 69-inch, 68-inch kind of level. And most females are maybe somewhere like 63. That's where the most of them are. But obviously, there are some very tall females heading up well over 70 inches. And there are some fairly short males. So this is 10,000 data points here. Well, we want to ask, do the heights differ between these two? Okay, so we're going to apply students' t-test. All right, interesting fun fact and history time. Students' t-test is called students' t-test because it was made by a really important engineer who was working for the Guinness Brewing Company. You know, the people in Ireland who make that really thick, dark beer. So, dang it, the dude's name is, of course, completely escaping me right now. But I should be able to tell you it, and Wikipedia can certainly get you there. This well-known engineer was looking at differences between batches of beer. And he needed to know, does a given process really change the outcome of a beer? So he needed to invent a test called students' T. And why was it called student? Well, he really wanted to publish his work. This was like something like 1920 or 1918, something like that. And he wanted everybody to know about this really cool tool. And Guinness was okay with it being published as long as it couldn't be traced back to Guinness. They didn't want their company name attached to this for some reason. So he signed the journal article where he introduced this as a student. Just a student of statistics, right? You don't need to know my name. So at any rate, that's why it's called students' t-test. And the T, oh man, the T is the name of the distribution that's used in the test. So don't worry too much about that. But at any rate, what are the assumptions? History lesson is done now. We've learned that this is all really about beer. Okay? What do you need to know about the data to know that you can use a t-test? All right? So t-tests are only good for data which is continuous. All right? If the numbers are discontinuous or if they are discrete, this doesn't work. The data have to be normally distributed. So that's why things like, say, counting numbers don't really work with a t-test, because there can be no normal distribution. There's nothing less than 1 or 0 in a counting number if you're using positives, right? There's, if the data is uniformly distributed, just a flat thing, t-tests don't work. If data is exponential, if it's got a super long tail or highly skewed, t-tests don't work. Okay, so you have to see that your data you're testing, A and B, are normally distributed. T-tests only work if you have several data points. If you're trying to test 4 data points for males and 4 data points for females, good luck on that one. Okay? And of course, importantly, the two groups, the males and the females, they have to have the same variance for us to compare their means. So let's take a look. Do we meet all these assumptions with this data? Well, the data are continuous. There's, inches have decimal numbers and they can be anywhere in between. So there's an infinite number of them and they're all continuous. They're not broken up. The sample size is quite large. There's 10,000. So like a typical rule of thumb is that the t-test is maybe good in the range of above 30, right? So I think 10,000 will do. The variance is also roughly the same. Look at these bar plots embedded inside, okay? Sorry, not bar plots, box plots. So these box plots that are showing you the distribution of most of the data, right? The edges of the box show you that half of the data is within that box, okay? So those boxes are the same width. So these two distributions, the male and the female height distribution, they seem to have roughly equal variance. And importantly, the shapes of these are consistent with a normal distribution. They don't look wacky or exponential or something like that, right? Doesn't look like, say, that, which would be a kind of beta distribution, right? And it doesn't look, highly discontinuous, right? Those things would be bad. Okay, so it seems like this meets all the criteria we need. So, where is the mean? So women are around 63, men are about 69 inches. Let's plug it in. All right, so the t-statistic is what we have to calculate here. And it's going to be calculated from all the data points. Or you can potentially calculate it from things like the mean and the standard deviation. Okay? Now, the t-statistic is a table you look up, and once you get that statistic, it tells you something called a p-value. Okay? It also enables you to find out what is the 95% confidence interval in the means, the true difference of means. All right? So what does all this information mean? Well, the p-value here says that you have, so this is 1/10 of a percent chance of getting this just by random chance. So what that's saying is that to have two things be this far apart and not actually have a difference between them, like they really actually just come from different rolls of the same dice, right? So if you roll dice multiple times, you will get a wide range of numbers on those dice. But to get a number which is just insanely wacky, right, from the dice is rare. You're mostly going to get roughly the same numbers, right? So it is possible to get really big differences by chance. Okay? But this is saying that it's 1/10 of 1% chance to get a number this big. Right? And that is the difference between males and females, right? And what this says is that we can be relatively certain that the difference here is somewhere between 5.4 and 5.2 inches. Okay? If we did this experiment with a whole bunch of new men and women, we would get probably a slightly different number for the difference. It wouldn't be exactly this 63 and 69, right? We might get a decimal point difference, right? So we would get another measurement for the difference between males and females. But if we did this a gazillion times, then we would expect that 95% of those gazillion, that difference was between 5.4 and 5.2. All right? These are the tools of checking whether something is falling under the same, whether A and B, where A is women and B is men, whether those are truly different or whether they're actually the same thing, but just by chance, just by the random roll of the die, they look different. That is the question. And when this p-value number is very, very low, then we can say that is highly unlikely to occur if they're actually the same thing. Okay? So in this case, because this number is ridiculously small, 1/10 of a percent chance, we can say, yes, by a given criteria, we think that men are truly taller than women, that there is a height difference between them. So again, let's just review. That p-value is the magic thing. When that p-value is very, very small, we're going to say there really is a difference between group A and group B. There really is a difference in the health outcomes for diabetics treated by this medicine versus diabetics in the control group. Okay? And when that p-value is small, we feel very certain that there is truly something happening here, that it is highly unlikely to be just random weird chance. Okay? How do we understand p-values? What do they really mean? Well, let's imagine we're flipping a coin. We're going to flip a coin 16 times, right? It's a 50% chance every single time that it comes up heads. So what is the expected number of heads? The most common number of 16 flips, the most common number will be half of 16, which will be 8. Right? So this is a distribution of such a thing, right? So we can see here that 8 is the most common number, and it falls off with the expected bell-shaped curve, right? It's relatively likely to get a 7 or a 9 head situation because coin flips are random, but we're very unlikely to get a 12. 12 flips landing heads out of 16 times would be a relatively rare event. Okay, so 40% of the time, we're going to see 8 heads and 8 tails, just like we said. So the p-value, when we say the p-value is something, what we're looking at is the probability of getting these results or weirder results just by chance alone. So we're going to do 2 sets of 16 coin flips. And we get 8 one run, and we get 14 the next run. Is that 14 so outrageous that we should say, I don't think we have a good coin? Our coin must be biased. It's not the same coin as the one we used to flip 8 heads. All right, that's our question. So, oh, I misremembered the numbers. So in the trial, we're going to get 10 heads. What's the probability of getting 10 heads? Well, the probability of getting 10 heads is just this amount, right? Okay, but we're also going to go both directions. We're going to say it's also the probability we're interested in of getting 6, which is the same distance away from the mean, right? So we're going to go from 8 out to 10 and from 8 down to 6. And we're also going to ask, what's the probability of everything else that's out here? Okay. So, and we're going to take all those probabilities, we're going to add them all up. Okay. So these are the total numbers of flips: 60,000, 5,000, 2 out here on the 14, right? We're going to add them all up. And then we're going to find out what's their probability out of all million coin flips. Okay? So we're going to add up all those numbers, and we're going to find the mean. We're going to divide it by the 1 million coin flips that were done here. So we're finding that the total probability is 133,000 roughly out of a million. So that turns out to be 13%. So everything out here constitutes 13% of the possibilities that are going to happen. Okay? So the p-value is 0.133. It is that there's 13% likelihood of getting numbers 10 or weirder, right? When you do this experiment, when you flip 16 coins in a row. So that is the p-value, the probability of observing that result by chance. Now, if you found that you got something way out here, you would find out that that p-value is something very, very tiny, like maybe 1/10,000th of a percent. Okay? So it's highly unlikely to get that number. And so you might see, if you got that number, you might guess that this was not a fair coin. All right, so what if you observed 16 heads, right? The p-value gets really wacky out there. What do you think the p-value would be? Would it be less than the 0.13 we just discussed? Or would it be greater than? We are asking you which way an unlikely event is. Is it a high p-value or a low p-value? So once again, tonight, I'm not going to bother putting out the quiz stuff. I apologize for that. You're going to have to do this in your own head. So the correct answer is, of course, A, which I didn't write down there, but yeah. So unlikely events like getting a 16 out here are highly unlikely, and that means that their p-value is going to be something like, I don't know, 1 times e to the minus 20. I don't know. I'm making that number up, but it's going to be unlikely. So when we see something like this, we see a p-value 0.001, we know that that's an unlikely result, less than 1% chance, 1/10 of a percent. Okay? So we think that there is strong evidence that this is something which there is a true difference there. Men really are a different height than women on average. Right. So let's use all your knowledge in this little self-quiz. Right? Take a look at these distributions. Tell me, do you think a t-test would be appropriate or not? Well, the question says not, so obviously it's not appropriate. But what would be the reason why? I'm going to let the cat into the office. You can probably hear him meowing outside the closed door. And you have a think about which one of these, A, B, C, or D, are the right answer. Say hello, Magic. You're just happy to be giving attention. All right. Go over here on the couch. All right. So the answer is, oh, I didn't put the circles on. All right. Well, the problem is the unequal variances. Okay? B. You had a long time to think about that. Sorry about that. All right. So let's take a look at these two. Would a t-test find a significant difference in the means? Take a look at A, B, C, and D as your options. Would the t-test find a significant difference in means between this curve representing the Congo and the curve representing Denmark? Magic still has a lot of things to say. Well, there's kind of two answers here. So these are very, very well separated. And therefore, in one sense, the answer would be yes. They would find a difference in means. But they're so well separated, right? They hardly overlap at all. So it's pretty clear that there's a difference there. Oh, here comes a cat. Right? Yeah, Magic, you don't want bourbon. So, however, the other thing is that the t-test is really not appropriate because this variance and this variance are quite different. All right, Magic, yes, you can rub up against the iPad. It is your iPad now. You have claimed it. All right. Get your bottom out of my camera. All right, so that's all I had for you on comparisons of means. I'm going to take another little break, and we'll come back here in a few minutes to cover regression on another video. And maybe by then the cat will stop getting in the way. All right, bye for now.